Shall we? Good afternoon. The last time we talked about reduction and oxidation reactions, redox reactions, and you have hopefully seen that there is no reduction of one thing without an oxidation of another. Because reduction, what does it mean? Reduction is, what I said, Leo goes Ger. Reduction is what? It's a gain of electrons, okay? You have a higher oxidation state, and then you add electrons to it, and then you get a lower oxidation state. Is that what a reduction is? Okay, it gains electrons and will be reduced. So we had Leo goes Ger, loss of electrons is oxidation, and Ger was gain of electrons is reduction. And when we had oil rig, oxidation is loss, and reduction is gain of electrons. So we then looked at a reaction where we have zinc, a zinc metal, piece of zinc metal, and a 1 molar zinc sulfate solution. That means the zinc metal has oxidation state what? Zn has oxidation state what? 0, exactly. And zinc sulfate solution, what's the oxidation state of the zinc ions? 2+, okay. All right, oxidation state is 2+. So we have zinc metal in a zinc sulfide solution, and we are at standard state. We talk about standard state. We say this is 1 molar, okay? Now, the other half cell that we have constructed, this was this one. The other half cell where we had copper ions, copper sulfate, 1 molar, in contact with a copper stick, a copper metal rod, okay? So what's the oxidation state of the copper metal? See, up there, oxidation state of the copper metal. Anybody help me out? Oxidation state of the copper metal. Copper metal. Who said it? 0. 0, exactly. And oxidation state of the copper sulfate, the copper in copper sulfate dissolved in solution. What's the oxidation state of the copper? 2+, +2, okay? So we have zinc, oxidation state zinc cations, oxidation state 2+, copper cations, oxidation state 2+. What would be the oxidation state of copper if it would be copper plus? What would be the oxidation state? +1, okay? But it's not 1+, it's 2+ in this case. Okay, and the zinc metal has oxidation state 0, and the copper has oxidation state 0. So if we have this reaction here, and we know, because I told you, this reaction goes into the right direction. That means delta G is smaller than 0, with this K would be much larger than 0. K would be much larger than 0. That means you're making much more products than you have reactants. So it's spontaneous from left to right. So what actually will happen is the zinc metal goes in solution. Here the zinc metal goes in solution to make zinc 2+ ions, okay? Now, the zinc metal goes in solution for zinc 2+ ions plus 2 electrons, okay? We have these 2 electrons, they're left on that surface of that zinc metal here, because it just went a zinc 2+ in solution, and the 2 electrons hanging around here on the surface. Of course, it's more than 2 electrons, because not one molecule only will do that, 1 atom will do that. But let's just look at 1 atom. So they hang here, and on the other side, the copper really would like to get 2 electrons. The copper 2+ would like to get 2 electrons, so we connect this here and let these 2 electrons flow along here. Now this is negative, with 2 electrons negatively charged, so the copper 2+ will pick up these 2 electrons and will plate out as copper, all right? So that's the red cat. That's the reduction. The reduction, the copper 2+ gets reduced by picking up 2 electrons to copper metal. And in this way, it plates out onto the copper electrode. So the copper electrode over time should become thicker, okay, or heavier, because all this copper plates out. Is that clear? All right? But the zinc, what happens to the zinc? When is that reaction done? what happens to the zinc? The zinc does what? It disappears, it dissolves. So when all the zinc metal is gone as zinc 2 plus in solution, the battery is dead. All right? But there's one thing which we need to consider still. So we started out with 1 molar zinc sulfate solution. So the concentration of zinc 2 plus was 1 molar, and the concentration of sulfate ions, negative ions, was 1 molar. But now we are dissolving zinc 2 plus into that solution, so we're making an imbalance. The sulfate minus cannot balance the zinc anymore because we're having too many positive zinc ions in solution. All right? And here we started out with 1 molar copper sulfate. The copper at the beginning is 2 plus, and it's 1 molar 2 plus ions. Okay? But now it plates out here, so that means the 2 plus ions go away, they become copper, so you become deficient in positive ions. The sulfate ions haven't changed, but the copper ions are disappearing. With this, you have an imbalance too. Too much negative charges here and too many positive charges here. So this is why you need that salt bridge, and that salt bridge has an anion and a cation, is potassium nitrate, K plus, NO3 minus, and this is unbalanced. There's too many positive charges. So what will happen? The nitrate will diffuse in here, the NO3 minus, to have a charge balance. And here the potassium will diffuse in here because the copper is going out, the 2 plus is going out. So we have too many SO4 minuses here compared to the positive charges. So the potassium will diffuse in here to give you the charge balance. Okay? This is why the salt bridge is necessary. And we're going to be a big salt bridge today in a week, all right? I'm already preparing for it. I don't know quite how I'm going to do this, but with all of you holding hands and so on. Maybe we do this successively. First a couple of rows, and then a couple of rows more, and so on. It's going to be fun, okay? All right, so, and then we said we have this reduction, but we can measure now a whole bunch. This is called a half cell. This is 1 half cell, and this is the other half cell. You have to combine 2 half cells with each other to get a voltage out, and this is then called a galvanic cell. And if this is at standard condition, each 1 molar, it's a standard galvanic cell. Now you can combine any old half cells with each other, and there's a whole table of half cell potentials. And they're all written as reduction potentials. And so we have, for example, copper 2 plus gets reduced with 2 electrons to copper. This is a positive potential. And this was our hydrogen. The hydrogen ion, the H plus, gets reduced, 2 of them gets reduced by picking up 2 electrons to hydrogen gas. Oxidation state 0, oxidation state 0. Goes from +1 to 0. Goes from +2 to 0. The zinc, for example, goes from +2, picks up 2 electrons, goes to 0. So all of them are written as reductions. Okay? Now, the point that you need to understand is that if the more positive it is, the stronger an oxidizer it is. And oxidizers like to pick up electrons from somebody to be in the reduced form. So this, the more positive one goes in this direction, and the other one becomes the reducer. And the one below, the reducer gets oxidized. So in this case, the hydrogen would be the reducer. It gets oxidized to H+. So this would go this way. This is 0.34 volt. This goes this way. That's the more positive. And this goes that way. All right? Nevertheless, they are written all as reduction reactions, but one will be the oxidation reaction. That will be the one with the more positive potential. And the one below, whatever below, doesn't have to be negative, just a number smaller than this 0.34. This will be the reducer that gets oxidized, and then it goes in this direction. So when this gets oxidized, it furnishes these 2 electrons to here, or this here rips off these 2 electrons from this here, okay? So this goes in this direction, and this goes in that direction. Now, if you look, for example, copper could be reduced by zinc, and zinc would go in solution, and copper plates out. This is what happens here. You see that? Zinc. And copper could also be, or we can say H plus could could oxidize zinc. So this H plus gets reduced, and this one goes this direction. So the one above goes to the right, the one below to the left. This is how simple this is with redox reactions. So we have a whole slew of reactions here, and this is a standard table. I don't show you that table yet, because I want to first ask you a question and see if you have understood what I just told you. So which of the following will oxidize hydrogen, and which of the following will be reduced by hydrogen? And there's only one answer. It's not the Nitsche trick question where there are two answers. There's only one answer, okay? So is it copper 2 plus, copper metal, or zinc 2 plus? So here is our potential, your potentials. Why don't we put that one up here, please? The left panel up here. And I'm going to put this up here. There you go. All right? Which one will oxidize H2? Oxidize H2. It goes from 0, oxidize, 0 to plus 1 if it's H2. And which one will be reduced by H2? We're going to do this all lecture today, till the cows come home, okay? No, till you get it. Didn't I start it? Or? I did start it. Is that your answer? Why don't you all click in? Give me an answer. Give me an answer, especially this guy here. This guy. I'm excited about these 4 people. These are the winners. You always have some of those. Got to have winners in the class. Huh? Okay, so is everybody in? Okay, I stop it now. And so why don't we discuss this? So there is 31% is a minority. There's a majority of 67%. Why don't you discuss this with each other? So which one will be oxidized hydrogen? So if hydrogen is oxidized, this is the reduced form, this would be the oxidized form. Now, would that be copper metal? Copper metal, oxidized, which of the following will be reduced by hydrogen? Which of the following, reduction by hydrogen, okay? So, and this is copper, this is metal already here, all right? Why don't you think about this and give me an answer? Let's see if this does it again. No. So far not. Discuss it with each other. I want the right answer from every one of you. Especially all the A's. The A's should give me the right answer. Yes, that's right. So Henry Doe says it's just like an acid becomes a conjugate base. That's exactly a very good analogy. Yeah. Yeah, exactly. Okay, are we all clear on that? Now we have a count here of 218, 219. So the electrons didn't want to do in this machine what I wanted them to do. Wouldn't it be great if somebody could influence this with its cell phone? I shouldn't have said that. Okay, I go with A, all right? Not much change. So, let's have a look at this. Which of the following will oxidize hydrogen? Oxidation of hydrogen goes this direction, okay? So only the one above can oxidize it, isn't that right? So this goes this direction, and this will go this direction. So this one would not, if this goes in this direction, then this one cannot go in this direction, okay? But it's below, so that doesn't work. So copper metal doesn't do anything, okay? Copper metal can only be oxidized. Copper metal is out. Now let's zinc. Zinc, this would be the oxidation, okay? And the reduction would be this, but this has a more negative potential, so it's not an oxidizer. It's a reducer, okay? Which of the following will be reduced by hydrogen? So obviously, copper 2+ rips these electrons, these 2 electrons off of the hydrogen. The hydrogen becomes 2H+, and with this, the copper 2+ becomes copper. So what's the potential of such a cell? There it is, okay? So this is the copper. It will be reduced, and this will be oxidized. I reversed this here, but since this is 0, it doesn't matter, okay? 0 plus 0 or minus 0, if I add them up, it's 0.34 volts. This is 0.34 plus this here is 0.34 volts. What do you think delta G is for that reaction? Positive or negative? Delta G is minus N times F times E, okay? And if delta E is positive, then delta G, because it's minus N times F times E, it has to be negative. Delta G, it goes exactly into this direction, and the answer with this was this one here, okay? There you go. Now, of course, there are more than a couple of standard potentials, or the 3 that I have shown you. There's a whole slew of standard potentials in the back of your book, standard reduction potential, and they're all written as reduction, okay? The more positive ones oxidizes the more negative ones, but it doesn't have to have a negative sign necessarily. The higher ones, the higher the number, the stronger the oxidizer, okay? Manganese, for example, can actually oxidize gold. With manganese, you can oxidize gold to gold 3+. Gold is a very noble metal, and it's very difficult to get gold in solution. That's why you have jewelry, which doesn't dissolve in anything, essentially. But don't bring it to manganate, okay? All right, so we're going to talk a lot about balancing redox equation, and I'll give you a couple of examples for this. So you see this is the list here, and there are positive to very negative. So what the preferred state of manganese is obviously Mn2+, because it's positive. The more positive, the better an oxidizer. That's the preferred state of gold. What's the preferred state of calcium? Is calcium 2+ the preferred state, or calcium? Ca2+, exactly. That's the preferred state. The more negative, the more of a reducer it is. It wants to be in the oxidized form. The oxidizer wants to be in the reduced form, and the reducer wants to be in the oxidized form, okay? So this one, for example, can oxidize silver. See that? Actually, this can oxidize anything below, anything. So let's have a look at this here. And this will help you balancing redox equations. So you can have these equations, something like this here. That's a nightmare, okay, to get the stoichiometric factors right here. So you could say this by trial and error. You'll be sitting there forever to balance this equation. So, but you can use the standard reduction potential, and you see the MnO4- gets obviously reduced to Mn2 plus. The manganese, what's the oxidation state of the manganese here? How do I get to this? Oxygen is -2, okay? I have 4 oxygen, 4 times -2 is -8. I show 1, so it still is -7. So what is the oxidation state of the manganese then? +7. Oxidation state goes from +7 to +2. So how many electrons would you need to get from 7 to 2? 5 electrons, okay? This is a reduction, obviously, and this is exactly this reduction here, all right? And then we have another one, bromide gets oxidized to bromine, liquid bromine. Bromide, what's the oxidation state of bromide? -1, and bromine, 0, okay? So now let's manufacture this out of 2 half cells. We use that half cell here, let's write it, MnO4 plus 8 H3O plus 5 electrons gives Mn2 plus 12 H2O. Okay, that's the first part. Now we need to find a second one where we have Br minus and Br2 in there somewhere, and lo and behold, it's right here, okay? Br2 liquid plus 2 electrons gives 2 bromide ions, okay? 2 bromide ions. So now, if I add this up, I don't get this here. So obviously I need to reverse this one here. And I also need to find the common denominator for the number of electrons, because the electrons need to cancel. One gives it, the other one takes it. It needs to cancel. So what's the common denominator for the electrons here? 10. So I would multiply this by 2, okay? So then I have 2 MnO4 plus 16 H3O plus 10 electrons plus 2 MnO2 plus 24 water. You're drowning, there's so much water, okay? Plus 24 water, and so this would be the common denominator would be 10 electrons, would be plus 10 electrons on this side. Now, what would I have to do with this one? I multiply this by 5, so I have 5 Br2 plus 10 electrons plus 10 Br minus, okay? But this is written wrong. I need to have this on this side here, okay? So I multiply it with -1, so that gives the 10 electrons. Now let's see, first the 10 electrons, okay? So it's 10 Br2 plus 5 Br2 plus 10 electrons plus 10 Br minus, okay? Now we have 10 electrons here and 10 electrons here, okay? So, but now I have to reverse that, okay? This is 2 Br minus, no, this is 10 Br minus plus 10 Br2 plus 2 electrons, plus 10 electrons, okay? So these electrons cancel here. Now I have multiplied this with 2, and I have multiplied this with 5. So now the electrons cancel. I have 10 here and 10 here. So now I can add this up, okay? I have MnO4 minus, how many I have there? 2 MnO4 minus, plus twice H3O plus is 16 H3O plus 5 times 2 is 10 Br minus. And these 10 electrons here cancel against these 10 electrons here, so I can take this out and this out. So now I have multiplied this with 2 is 2 Mn2 plus 24 H2O, and this I have multiplied with 5 plus 5 Br2, okay? With this you have your reaction done. What do you think the potential of such a thing would be? Okay, let's do that. First of all, you do not multiply potential with stoichiometric factors. No, not like you do it, not like you do it with delta A, with H's and G and S, where you multiply with stoichiometric factors. Potentials are not multiplied, okay? So the potential will always be the same, even if the stoichiometric ratio gets higher and higher, as long as it's in the same ratio, okay? So what was that? So this is a potential of 1.49 volts, and this is a potential of 1.06 volts. But we reversed that, didn't we? We reversed that. What was the potential then? Minus 1.06 volt. Plus 1.49 minus 1.06 is 0.43 volts. Is that right? That's what that potential should show if I put 2 cells like this together. And the potential is 0.43 volts. So you know how to handle that. So the reducer what is the reducer gets oxidized and becomes an oxidizer. Yeah? Or the oxidizer gets reduced. Yeah? That's what we did here. Which is the reducer? Which was the reducer? This was the reducer. It gets no. The reducer gets oxidized. The reducer gets oxidized. Goes from -1 to 0, and it deliberates these electrons, and these electrons are picked up by the oxidizer, which gets reduced. All right. So, what is the delta G of this here? Positive or negative? Negative. Okay. So it rolls down free entropy, free energy hill. So minus n times F times E, delta E naught. You know, that's why we have that naught here. E naught is the standard potential. That's why there's a naught there. I mean, you had some homework maybe where you, no question. We had some homework where you maybe had not at standard state. Was there some homework, or did we take it out? You haven't done the homework yet, okay? All right, good. So there it is, delta G naught is n times F times delta E naught. That means that the potential is at standard state conditions. So let's do another example. Rusting of iron. Iron is an oxidation. Iron gets oxidized by oxygen. Gets oxidized to what? Iron is 0. Can be oxidized to iron 2, let's say. Okay? Iron 2 is an oxidation. All right? And this oxygen does that. And with this oxygen plus iron plus water gives iron 2 plus OH minus. That's a possibility. So it's rust, actually. Okay? This will make an oxide later. And so this is the rusting of iron. Let's see how we can fix that equation. If we can find two potentials, two half cells, to figure that out, how this goes. Yes, sir. Yes, ma'am. Huh? You get the whole chart. You need to bring your magnifying glass to see it. No, I'm just kidding. You will get, in the exam, you will get a whole page with these potentials, the reduction potentials, okay? They're also in the back of your book, but this will not help you because it's a closed book exam. So we want to look at something, iron. Let's look at iron. Iron is here, and Fe2 plus is here. So we use that baby here, okay? Fe2 plus 2 electrons gets reduced to iron metal. That's not what they want to see here. So let's see if I have something else here. So there's something with OH I need, okay? Oxygen and OH. There's O2 plus 2H2O plus 4 electrons gives 4 OH, okay? There it is, 0.4 volts, 0.4 volts, okay? So now we're going to look back for our iron. Nope, wrong direction. There's our iron, so that's a negative potential, very negative potential. So because iron likes to be in this, likes to rust, okay? Likes to be in the oxidized form. That would be great if iron would have a very positive potential, would be very valuable iron, very noble iron. But no, iron is not noble at all. It likes to rust. It likes to go into this direction. So we have Fe2 plus 2 electrons gives reduced iron. This is 0. This is plus 2. Okay, and this is minus 0.41 volts. So what is our common denominator? 4. So we have to multiply this with 2. So we have 2 Fe2 plus 4 electrons gives 2 Fe. Yeah? And then we have to multiply it with minus 1 also. Okay, by 2 and minus 2 actually. With this, I change the potential from 0.41 from minus 0.41 to plus 0.41. So now we are going to add it up here. So we have 4 electrons here, 4 electrons here that can cancel. We have oxygen here, 2 waters here, 2 iron here, 4 OH here, and 2 Fe2 plus here. Let's see if this is right. There you go. What's the potential of that baby? 0.81 volts, okay? So you would have, for example, a half cell. Of course, you don't make a half cell like this. Where you have on this side, what side would that be, the anode or the cathode? What would that be? That's the anode, exactly. Red cat. Cathode always to the right side. Reduction. So the reduction, so this is the oxidation. That means You have iron metal in contact with iron solution, iron 2+ solution. This should have to be 1 molar. You have a bridge, and then you have a 1 molar OH solution where you flush oxygen across a platinum electrode. So that will be the red cat, the reduction. So we go, okay, we go oxygen from 0 to oxygen to what? What's the oxygen here? Oxygen is 2, so it's -1. Okay? All right. Good. Who has a boat? Or whose daddy or mommy has a boat? Nobody? Only poor kids here today? It's Berkeley, huh? Not Stanford. Stanford, they would have raised their hands. Welcome. I don't have a boat either. Don't need a boat. Okay, you're not poor kids. All right. But, so if you have a boat, I'm going to get letters for that. But you know that it was meant in good spirit, okay? You have a boat, you put some sacrificial metal on it. Sacrificial metal, the propeller shaft is made out of iron usually, and iron rusts. Iron makes iron oxide, goes from iron 0 to iron 2+, okay? You want to prohibit this. So you use another metal, a sacrificial metal, which you let rust, okay? The sacrificial metal can be something. What could that be? If I want iron to be always in this side here. Any metal below would be sacrificial metal, wouldn't that be? So what would be? Could you use zinc? Yeah. You screw a strip of zinc in there. Make sure that you don't use iron screws because they will rust away and then the zinc falls off. So you use a zinc strip, you screw it to the propeller shaft, and with this, the iron will go in this direction, so the iron will not be oxidized, it will always be reduced, and the zinc will be oxidized. So the zinc will dissolve and dissolve and dissolve. With this, it prevents the propeller shaft to rust. And after a year, when you dive under there, or you lift your boat up, you put a new strip in there. That would be zinc, or you can also use magnesium. Magnesium metal, again, the iron goes in this direction, the magnesium gets dissolved, and we sacrifice that magnesium metal, and we call it a sacrificial electrode for iron. This is also in pipelines, they do that, and so on, that the pipelines don't rust. They put all kinds of sacrificial metal strips on there. Okay, so no boats. Autoionization of water. What is the autoionization of water? That's obviously H2O dissociates in OH minus and H3O plus. That's the autoionization of water. So we have 2 H2O gives OH minus and H3O plus. What's the K for that? Anybody remembers what the K for that is? 10 to the negative 14. So the equilibrium is with the reactants, isn't that right? So water doesn't dissociate a whole lot because you have only 10 to minus 7 moles of H3O plus and OH minus at 25 degrees. K is very small, okay? So that's the autoionization of water, is that? I write H3O plus OH minus 2H2O. What's the K for that? Come on. Whoever says negative gets shot immediately. 10 to the 14, okay? With the dumpling gun, okay? All right, so this was 10 to the minus 14, this way. But this way is 10 to the 14. It's all water, not very little of this one here, okay? This is 10 to the 14. Now let's try to construct something like this. Also, this is really not a redox reaction because I don't see any changes in oxidation state. We can do the following. We use this here. We use H2O plus 2 electrons gives H2 plus 2 H2O, or we can multiply this also with 2 here. And so I think that, yeah, this is how many electrons? I think there's one too many, but it doesn't matter. Okay, so this is 0 volt. It can be plus or minus 0 volt. If it goes in this direction, it's minus 0. If it goes in that direction, it's plus 0. It's the same. That's the nice thing. This was our reference system. Remember? Standard hydrogen electrode. Can go this way or that way, will be always 0. That's how we defined it. That's all there is. And then we measured everything against it, and some of them are more positive, some are negative, some are different positive values we get and different negative values. And this is how we construct something like this. Can you put this up back there now, please? This up here. Thank you very much. All right, so that's our first equation, and then we need to find something. What would that be? Let's see if there's anything with OH, something, OH, 2H to H to OH minus, there it's right there, okay? 2H2O plus 2 electrons gives H2 plus 2H minus, okay? This is minus 0.83 volts. What's the common denominator? Oh, this is convenient, it's 2, okay? So we need to reverse this, or don't we? Don't we need to reverse this here? Because we need that OH minus here, we reverse that. It becomes plus 0.83 volt. So now we can add it up. So what would that be? 2H3O plus, that H2 cancels, this cancels, and this is 2OH. Didn't I multiply anything? Let's see, what's that? Yeah, I can divide it, of course. I have 2H3O plus and 2H minus, and 4H2O. I divide it by 2, then I have H3O plus OH minus divided by 2H2O. Okay? See? What's the potential of that? 0.83. Okay? So is this a spontaneous reaction? Yes. So water itself doesn't spontaneously go very well into this direction, OH minus, H3O plus. It's 10 to minus 7 moles per liter. 10 to minus 14 is the K if I go in this direction. So how would that look like? My anode would be a platinum electrode and hydrogen gas and 1 molar OH minus, salt bridge. Then I have H3O plus at 1 molar, hydrogen gas, and a platinum rod again. Okay? This would be that cell that would generate 0.83 volts. Okay? Good. Now let me ask you. Let's see if you have the right stuff here. Nickel and silver and bromine. No, that's not enough. Let's see what we do here. Nickel and silver. You need this one here. If I could have this one up here, please. So I'm going to ask you the question now. If I could have the left panel, please, on the main screen, on the top screen. I ask you the question now. Which of the following will oxidize nickel but not silver? Oxidize nickel but not silver. So bromine is here. Bromine goes to bromide. That's an oxidizer, has positive potential 1.06. Then the next one is copper. Copper 2 plus 2 electrons gives copper. But the question is this here, okay? And then I have H3O plus 2, that must be this here. That must be 0. Now let's find out where nickel is. Nickel is here. Will oxidize nickel. Oxidize nickel. So it has to go into this direction. Oxidize nickel. And where is silver? Silver, don't want it to be oxidized. I want to oxidize the nickel with one of these 3, but not the silver. Not the silver, okay? Think about it and give me your answer, please. Do you know anybody with a boat? Good, okay. Look at the propeller shaft, so to speak, okay? All right. So what's the highest potential? That can oxidize everything below. But that's not what you want. You want it to oxidize nickel, but not silver. It's a handy stuff, this reduction potential, once you get the hang of it. That's, yes? Yes? I don't know. We will discuss it. I didn't quite understand the question at this point. Let's see if you understood the question. Which one can oxidize nickel but not silver? Oh, that's interesting. That's good to be expected. Okay, you got the hang of this, that obviously the most positive is Br2. That goes into this direction. It can oxidize everything below. Okay? Br can oxidize, it can oxidize this here, can oxidize this here, can oxidize this here. But the next one is copper. Can this oxidize anything? No, it's copper, not copper 2 plus. Okay? I wrote copper, not copper 2 plus. Is this an oxidizer, copper? Ah, okay. So now why don't you discuss this with each other and try to give me a right answer. So what is it, Henry? Henry says it's C. He's back. We were missing him the last time, didn't we? You don't have to apologize. You don't have to come here, okay? I'm not putting you on the spot. Maybe if I did, but this would be wrong. That's why we have it webcast. You can lay in bed at home and watch this. Fall asleep after 2 minutes. So do you agree with Henry? You agree with Henry? Wow. You got some fans here. How about you agree too with Henry? You agree with Henry? Henry said C. You agree with Henry? Good. We're having a big discussion here, obviously. Okay, let's have a look at it. Very good. Henry is right. And the 195 other people too. 194 actually. Okay, so let's have a look at this. These are the three oxidizers. We have bromine, liquid, could be, that's what I have here, could be reduced to bromide, has 1.06 volt. Everything below will be oxidized. So it will oxidize silver. It will oxidize silver. It takes these two electrons, or the electrons here, it rips it off from the silver and becomes silver 1, okay? So this is bromine, it oxidizes silver, so it's not bromine. Copper, we have already in a reduced form. It's not an oxidizer, okay? Copper 2 plus would be an oxidizer, but not copper metal. Copper metal is not an oxidizer. Copper 2 plus is an oxidizer. All right, this we can already eliminate. Now we have the only one, so this would be reduced in order to oxidize nickel. This works. This is 0, and this is 0.23 volts. So this goes in this direction, and the nickel goes in this direction. What's the potential at standard state of such a cell? Say it? Plus or minus? Plus 0.23 volts. That's correct. Okay? So this was the correct answer, as many of you had so rightfully. Now do another one. Which of the following will be reduced by zinc but not by bromine? So we have gold, copper again, and H3O plus, and H3O plus here. And then we have zinc. There's our bromine here. That's the bromine. We have bromide, okay? And then we have zinc metal. Zinc metal would be also here, okay? So I'm asking you, which of the following will be reduced by zinc? By zinc. Does it have to be above zinc to be reduced? I think so. But it should not be above bromine, shouldn't it be? Bromide, I'm sorry, it should not be above bromide. Why don't you think a little bit about this? I confused you thoroughly now, and now you can clear your mind and give me a right answer. Just a question formulated in a different direction. Okay, let's have a look at this. That's to be expected. That's why we are here. Well, let's think a little bit about this. So we have gold 3 plus. It likes to be in the reduced form, okay? So it would be reduced by anything below. So bromide would reduce it, wouldn't it be? Bromide would reduce gold, so gold would oxidize bromide, okay? And how about zinc? Will be reduced by zinc, but not by bromide. Zinc, okay, zinc should be oxidized. Everything above would be reduced, so this would go this way here, okay? Would be reduced by zinc, but not by bromide. So this would be also be reduced by zinc, and bromide, where is bromide here? Okay, is here. So what is it? Is copper, can copper be reduced? Can be an oxidizer that will be reduced? Okay, that's not right either. So why don't you think about this one more time, discuss it, and give me the right answer, please. So if it's reduced, zinc is reducing itself, it's got to be oxidized. We're talking now about a reducer. So the reducer got to be oxidized. It oxidizes everything above. No, it reduces everything above. What is it? Yes. It stopped, okay. Did it count? Yeah. Okay. Why don't you click in quickly, everyone? Give me your answer again. Okay. Everybody in? There's not everybody in. Come on, everybody in. I need to count you. Okay, 5 seconds. Done? We're not 100. No. Come on, everybody. Okay. I go with C. Okay. Let's go for it. Why? Which of the following will be reduced by zinc but not by bromine? So the reduction is everything above, isn't it right? The reduction is everything above. If I have zinc, okay, will reduce this one here. Okay, this will reduce it to where? to H2, okay? The HVO plus. So which of the following will be reduced by zinc but not by bromide, okay? So zinc, if it's reduced by zinc, zinc has to become oxidized. Is that right? Okay, so this goes this direction. So this would go this direction. That will be reduced by zinc. It will be going from plus to 0 here, okay? And what is the other one? Copper is out because it's already in reduced form. And the next one would be bromide, okay? Bromide would be gold, wouldn't it be? That would be reduced, and this would reduce it here. So it's got to be, which one got to be? This one here will be reduced by zinc here. That goes this direction, and this goes this direction. So the answer got to be C, if I'm correct. And it's true, okay? I see you. You got to practice this, all right? I'll see you on Friday.